This video is about decomposing rational expressions into partial fractions. With this example, 5x plus 16 over x plus 2 times x plus 5, we know that this rational expression, because it has these two factors, can be written as a sum of two fractions where each factor shows up once in each denominator, like this. Our job is to figure out what the numerators should be. For now, we'll call them a and b. We have what looks like an equation. It is saying that these two sides are equal to each other, but we're not trying to solve for x. We're trying to really figure out what a and b must be for this to hold true for any value of x. But for now, we can use some tools like we're solving an equation to really clear out these denominators. I'll multiply every term by the common denominator. And basically, what I see in this initial fraction, everything times x plus 2 times x plus 5. And I'm interested in not multiplying everything out just yet, but looking at how each denominator is canceled and what factors are left over in the numerator. So that will leave us with this equation, and again, we're looking for an identity. How will this equation be true for any value of x? One approach we can use to determine a and b would be to choose some value of x that might simplify this equation that we have. And I'm thinking about choose a value of x that would make an expression equal to 0, get it completely out of the picture. If we were to choose x equals negative 5, and remember, this is a statement that we want it to be true for any value of x. So if x equals negative 5, it should be true. And plugging negative 5 in place of each x, we're able to wipe out this term that has a, because the negative 5 plus 5 equals 0, and 0 times anything equals 0. So just a little technique we can use to get the a out of the picture and see that on the left side we have negative 9, on the right side the x equals negative 5 added to the 2, and then multiplied by b, which we don't know what it is yet, leaves us with this negative 3b. But it has to be true, so b has to equal 3, again, like I'm solving this equation. So we've figured out that the numerator of this fraction, the numerator b, has to be a 3, and if we choose a different value of x, maybe one that's going to cancel out the b and leave the a behind, so hopefully we're seeing x equals negative 2. And for this part, what we're doing is looking in each of these parentheses, these factors, and thinking what value of x could make the expression equal to 0. So our first choice was looking at this set of parentheses and seeing that a negative 5 plus 5 would equal 0. And now for our next part, we're looking at the second set of parentheses, x plus 2, we should choose negative 2, the opposite that will make it equal to 0. So we're plugging a negative 2 in place of each x. Back here, the negative 2 plus 2 equals 0. Everywhere else, on the left side, we've got a 6. On the right side, this turns into a positive 3a. Therefore, a equals 2. And now we have determined what these two numerators are so that we have fractions that add up to equal this fraction that we started with on the left. Let's put the 2 in place of a and 3 in place of b. And what we have here on the right side would be considered our answer. We have taken the original rational expression and broken it down into separate fractions that when they're added back together will give us what we start with. Let's look at a few more examples and point out where we have to take an approach that's different from what we were able to do with this first example. Next, 7x minus 5 over x squared plus 2x minus 15. We want to illustrate with this example that your denominator should be factored first. In this case, it's not coming to us in factored form. Let's do that first. X plus 5 times x minus 3. And now let's set up those partial fractions. One denominator using x plus 5, the other denominator using this other factor, x minus 3. In the numerators, we can place placeholders a and b, and now begin to clean this equation up. Clear out all the denominators, and we can maybe begin to do this step a little bit quickly because it's pretty consistently doing the same thing, accomplishing the same thing each time. It's able to get rid of this denominator from the original rational expression, and I have to think about, well, what would be left over? If the a is over x plus 5, it's clearing out the x plus 5, but the x minus 3 is left behind. when I look at the second fraction, the x minus 3 is there to simplify with this x minus 3, but the x plus 5 left behind. So here's the simplified equation. Next, I know I could choose some values of x that will make a term equal to 0. We could choose x equals 3, that would wipe out the a, or we could choose x equals negative 5, that would wipe out the b. But I want to take a different approach with this example because we will see problems in the future where that first method won't work. So we need to have a backup plan. It's a little bit longer in some cases, but it's something that always works. So we will see it again in future examples. What we'll do instead of choosing values for x, we'll actually distribute the a and b. When it comes to this a times x, we would just call it ax, and a times negative 3, we would call that negative 3a. Just like a and b are variables. We're not treating them any differently. It leads us to this equation. And now what we can do is something based on knowing that only like terms can be combined. 7x that we have here on the left side can only come from this ax plus this bx. There's no x in the negative 3a and no x in the 5b, so those are separate terms. So we're going through this equation, and we will parse out the different terms. First, we're just taking the 7x equals ax plus bx. All the terms that have x are forming their own equation, and at the same time, we're going to lose that x. All we really care about are those coefficients, because what is it about combining like terms? Ax plus bx, if we knew what those numbers were, we would add up a plus b. So 7 has to equal a plus b. We just lose the variable x. Now, we don't have enough info yet to figure out a and b. We've got two variables, so we'll need two equations, and that's where we'll go with the constants to find that second equation. Negative 5 must equal negative 3a plus 5b. We can say that they're all constants because a and b are about to become actual numbers. So there are no variables here. These are all constant terms, and there's the equation from those terms. At this point, you're thinking back to solving system of equations, two equations with two variables. Back to some earlier algebra moves. We've got methods of addition or elimination. People will call it one of those two usually. There's also the substitution method. With this problem, I'm going to choose to do a substitution. The first equation has a and b. I think I'll go ahead and just solve for a. So moving the b over to the left side, 7 minus b equals a. And now into this a right here, I'm plugging in 7 minus b. So rewriting this equation, negative 5 equals negative 3 times 7 minus b, and finishing up with the plus 5b. We were able to get rid of the a with that substitution move, so we will proceed with this equation to find b. Distribute the negative 3. Careful here where we've got two negatives equal a positive 3b, and b equals 2. We've got our first numerator, well, it's the second fraction, but the first one we've determined, it is a 2. b equals 2. And it is important that the 2 is the numerator of x minus 3. Don't get crisscrossed here. So when you first set it up, you might have a over x minus 3 with b over x plus 5, but our work here will always match up the correct numerator with its denominator. So the 2 really needs to show up over x minus 3. And whether that whole thing is your first fraction or your second fraction, that won't matter. We know addition, we can do that in any order. Okay, so let's move on and figure out what is a, and that's pretty easy with substitution. We're just plugging back into this equation, 7 minus b, so that's 7 minus 2 equals a. So we've got a equals, there we go, 5. And let's go back up to these numerators and replace 5 over x plus 5 plus 2 over x minus 3. There are those partial fractions. Now let's move on to another interesting example. In the denominator, we have a repeated factor, x minus 4. We see x minus 4 squared times x minus 1 in the denominator. And this plays a critical part in how we set up the partial fractions. The x minus 4 squared, this factor that is repeated, we actually need to have partial fractions using that factor to the second power and that factor to the first power. And definitely you're saying, well, wouldn't this really just be an x minus 4 times x minus 4 times x minus 1? Do I need to have this with the exponent of 2? And with this method, yes, we do. And if this was an exponent of 3, we would need x minus 4 to the third, and x minus 4 to the second, and x minus 4 to the first. Whatever the highest exponent is that we see, we need to have that in a denominator, and that same factor over and over again, but decreasing that exponent. So we have it to the second, and we have it to the first. And we'll still need one for the x minus 1. So that's not really too different there. It's like it has an exponent of 1. We only need to use it once. But a higher exponent, we need to do this move here, repeating the factor and decrease that exponent. Now we can still set up our placeholders a, b, and c. Let's get those in there. Now the next few moves are like what we've done before. I'll multiply, or think about multiplying this entire denominator to every term that we see, all 4 terms. The one term on the left side, basically it's just going to wipe out the denominator and leave the numerator behind. But carefully with what we have on the right side, these 3 terms, think about which factors will be left over after we simplify with what is in the denominator. With this first fraction, x minus 4 to the second is in the denominator. To completely simplify there, we're left only with x minus 1 times a. However, in b, we're going to see x minus 4, only 1 is simplified, so 1 will be left over. We'll have b times x minus 4 with the x minus 1. And over to c, the x minus 1 is gone, but x minus 4 squared is left behind. So here is our new equation with all the denominators simplified. We're choosing values because I think this way is a little bit quicker, and it's always the way I like to start off. We can always figure out a, b, and c by setting up a system of equations like we did in the last example. My preference is to actually do a little bit of each. I think it's easier to find a, b, and c when we choose values of x. So it's my video, we do what I want. But we'll get to a point where we do have to go back to that second method and try to set up a system of equations, or at least one equation. And we'll definitely see those examples in more detail. But I want you to know that my flow is I start off choosing values of x, which will cancel an a, a b, or a c. So if x equals 1, it's wiping out this term here, and it's wiping out b. And that's a key part for this part where I'm choosing a value of x. I'd like it to wipe out all of these letters except for one of them. I'd like it to wipe out b and c, or I'm sorry, a and b, leave behind c with this one. So let's do that. Okay, a 1 in place of each x. Left side, this is not so bad with subbing in x equals 1. And it's not so bad here on the right side either. There's the term equaling 0, and another term that equals 0. This is 1 minus 1 equals 0. Doesn't matter what's going on with this other factor and with b. All I need is one of my factors to equal 0. It's wiping the whole thing out. Times 0 equals 0. And over here, 1 minus 4, negative 3, and that squared positive 9. So positive 9c back there. So let's figure out what c is. The left side, everything sums to 18, and divide by 9, c equals 2. Can we see a different value of x to choose? And it's looking like 4. A positive 4 will wipe out the term with c. It will wipe out this entire term with b. It will leave behind a term using a. So that is helpful. Let's choose x equals positive 4. And just go cautiously through this part of 4 in place of each x. This term up front, understand that we're only plugging in a positive 4 that gets the exponent of 2. 4 squared would be 16. And now work in this negative sign to make that first term a negative 16. There's 56 and minus 31. Over on the right side, 4 in place of x leaves us with a 3a, and these other terms equaling 0 wiped out totally. We're working to find a, and a equals 3. There's our next one. Now going back to this equation that we have here, there's really no number we could put in place of x that's going to get rid of a and c, but leave b behind. So at this point, we need to multiply everything out. It won't be a full system of 3 equations because we actually have 2 of them figured out. So it's going to go pretty quickly. I'm going to FOIL the x minus 4 times x minus 1 first. And I know that this x minus 4, that's x squared minus 8x plus 16. And now I'll distribute a and b and c. I just like to take my time there, and especially back here, don't distribute this c first here and then squared, because that's making you do a c squared, and we really only have it there once. So make sure you're doing exponents first, and I like to FOIL also, take that out of the way first, and then distribute the letters a, b, c. Okay, ax minus 1a, bx squared minus 5bx plus 4b. It does get crowded now that we've got two linear factors here, but totally manageable. And here cx squared minus 8cx plus 16c. So the next part is that we parse out from these equations all of the like terms. If I start with x squared, on the left side, negative x squared, and on the right side of this equation, I have a bx squared plus cx squared. Now I can ignore the x squared parts and think only about the coefficients, that negative 1 must equal b plus c. Now I don't need to go through and go find all the linear factors because I've got c. I know it already. c equals 2. So negative 1 equals b plus 2. We'll solve this. b equals negative 3. And that's all we needed. We'd had a and c. So I avoided an entire system of equations by choosing a couple of x values first. But I did eventually have to do the move where I'm multiplying everything out and parsing out the specific terms, the like terms of this equation. But only enough to find what I need, that b equals negative 3. So we'll clean up our answer a little bit. And now we have the three partial fractions of the original rational expression. Moving on to our next example, thinking about, and I would always start out thinking, is this denominator factored, and is it factored completely? And in this case, we see this x squared plus 1, but we cannot factor that using real numbers. And we're trying to just work with real numbers with these partial fraction problems. So x squared plus 1 takes some special attention when we do partial fractions. And it's what we're about to see is what we would do for any factor in the denominator that is quadratic, that is a degree 2. And understand that it is not really like what we did with the last example where we had a repeated factor, an entire factor with an exponent. So it's different from what we just saw. It is the case when one of our factors happens to be quadratic, a degree 2, instead of the linear factors that we've been using so far. The move is, when we set up the partial fractions, that one denominator, well, let's get the x minus 7 out of the way. We'll have one denominator using x minus 7. The other denominator is going to take the x squared plus 1, and we only need it once because this entire factor, it's like it has an exponent of 1. It's not repeated, so we'll use it just once. But the way it works with partial fractions is that our numerators have a smaller degree than the denominator. So we've been assuming that our numerators would be numbers, and that was okay because each of our denominators was linear, a degree 1, and you could think of numbers as like degree 0. But now that we have a denominator that is degree 2, it is possible that our numerator could be a degree 1. It could be a constant. It could be a little linear expression up there. So we can still assume that over the x minus 7 is a number. We can use a. But to account for the fact that over a denominator that is degree 2, it could be a degree 1 expression up here, we will write bx plus c. Now, it could end up being a constant. In that case, we'll find out that b equals 0, but it's not always the case. Often we can get like an x plus 3 up here, a 3x minus 5, or whatever. It could be linear, so we use bx plus c. And it could be linear because all that numerator has to be is a degree that is less than the denominator. So a degree 2 down there could be linear up there. Okay, I think I've said that enough. Let's go back to our old flow and get this equation cleaned up. 10x squared minus 50x plus 10 on the left. The fractions on the right. X minus 7 simplified out of the first fraction, leaving an a times x squared plus 1. Over here, the x squared plus 1 gone, but the x minus 7 left behind. Now, can we choose a value of x that will help us find a, b, or c? This is looking like trouble, but we'll get to that in a second. Let's choose x equals a positive 7. That's going to wipe out b and c and have us find a, so that's very useful. Plugging a 7 in place of each x. Okay, 490 after the exponent 2 and then times 10, minus 350 plus 10. On the right side, okay, this is 7 squared 49 plus 1. That's a 50a. Over here, a 7 in place of this x would give 7 minus 7 equals 0. The whole thing times 0 equals 0. It's gone. And solving this, a equals 3. So we've got one of the numerators figured out. That's good. But do we have something we could choose that's going to wipe out a and b and leave behind c? Well, b and c are grouped together, so that's going to be difficult there. Not to mention, we don't have real numbers that would make this quantity equal 0. So at this point, we go back to multiply everything out and get some systems of equation, or at least one equation from those like terms. So let's clear this out. Now, since we do know that a equals 3, go ahead and put that there, and when we multiply out, I'll have a 3 already there in place of a. That's going to keep our system of equations more concise. So the left side is good. Distributing 3x squared plus 3. This will need to be foiled out, 2 by 2 multiply to give us the 4 terms, bx squared minus 7bx plus cx, and minus 7c. I won't worry too much about these like terms from the outer and inner. They'll take care of themselves in the next step here. We're parsing out the x squares. 10x squared equals 3x squared plus bx squared. So that's a quick one. 10 equals 3 plus b. And that's sufficient. We can find b right there equals 7. Now over to linear terms, and we can choose linear or constant. It looks like two different ways for us to figure out what c is going to be. I'll go with the x terms. Negative 50x equals negative 7bx plus cx. So pull that over and lose the x's. We know that b is positive 7. I'll plug that in right away. Negative 50 equals negative 49 plus c. So c equals negative 1. And now let's go back to the original partial fractions, get our new values in their places. A equals 3, we got that first. And now bx plus c is becoming the linear expression 7x minus 1. The b has always been the coefficient of x. We just determined that it was 7. C was the constant part of that expression. It's negative 1. So there is the numerator for that partial fraction. One quick comment. When we do arrive at these partial fractions that have more than one term in the numerator, it's possible that we choose to split that one up also. So just understand that when we do this move, we never split up the denominator. I mean, as you can tell, splitting up a denominator takes a lot of work. Keep this denominator intact and have it be the denominator of each of these fractions. We split up the terms into the numerator. And know that's coming from our rules about adding fractions or subtracting fractions. If the common denominator is there, we just combine the numerator. We're just doing the opposite and splitting it back up. 7x and negative 1 to leave us with those three partial fractions. Now we've covered most of the ins and outs of partial fractions. The examples that you will encounter, I'm guessing, will be handled by one of those examples we just looked at. But here's the last case that is kind of interesting. What you need to know about partial fractions is that we only attempt it when the degree of the polynomial in the numerator is smaller than degree of the polynomial in the denominator. The examples we've had so far, it has been the case. We didn't make a big deal out of it. But with this example, I will. The degree of our numerator is larger than the degree of the denominator. It means that we need to actually divide this out first and do partial fractions on the remainder. So your first look actually at these problems is just make sure that the degree of the numerator is smaller. If it's equal to or if it's greater, if this was an x squared expression up top, I'd still need to do a long division or some type of division first and do partial fractions on the remainder. So this example is to go through those steps. I'll set up a long division here. I'm too lazy to do a lot of rewriting, so I've just squeezed it in down here and ignore what we've got there. There's the division that we're doing. And real quick, my first run is I'm dealing with my term all the way out here and saying this term times what equals my first term here. I'll put that term up top, and I like to line up my terms by like terms. And then once I know what my first term of the quotient is, I'll multiply back down to all of these terms. So we ignore everything else with this first move, just dealing with the first term in the divisor and the first term in the dividend. Okay, x squared times x equals x to the third. Multiplying back down, x cubed minus 3x squared plus 2x, multiplying down to each of these three terms. The next move is a subtract. I always prefer to flip signs and add because I'm prone to sign errors, so I do that. It helps. There's those x cubed terms are canceled out. Negative 4x squared plus 13x, we're adding down. I can bring down this negative 7 and begin my next round. It's just like the first. X squared times what equals the negative 4x squared. So quickly through this, a negative 4 and distribute back down here. I did the flip signs and add, and here is the remainder. Now, do you remember how we set up the quotient and the remainder with these problems? There's the quotient x minus 4. We take the remainder, and it becomes a new fraction. It's exactly like if you make an irrational number into a mixed number. You take the remainder, and it becomes a numerator, and the divisor here is the denominator. So we've made a quick transformation from the original problem, which had a degree of the numerator higher than degree of the denominator. We do the divide, and the rest of the problem is just do partial fractions on this remainder here. We'll be sure to include x minus 4 in the final answer, but up next is partial fractions right here. We have a denominator that needs to be factored first. X minus 2 times x minus 1. Looks like it's not too crazy of a partial fractions problem. We'll get a over x minus 2 plus b over x minus 1. Think about multiply every term by this denominator, x minus 2, x minus 1. That's going to leave us with a cleaner equation, x plus 1 equals a times x minus 1 and b times x minus 2. Remember, when we're multiplying through here, we're thinking about the denominator being simplified by one of these factors, and the leftover factor is what's there. So the b has the x minus 2 as its leftover factor. The a has x minus 1 left over. Not too bad for us to, well, go either route, basically. If your preference is multiply everything out and do system of equations, that's great. I'm going to choose an x value equal first to 1 to wipe out a and leave behind b. On the left side, 2 equals 0 minus b. That 1 minus 2 is negative 1, so negative b. So 2 equals negative b, b equals negative 2. We've got a numerator figured out. Let's choose x equal 2 to get rid of b and figure out a. So that leaves us with 3 equals a times 1, 1a. There's a equals 3. So let's wrap it up, put our final answer together nicely. There's the original fraction. We did a division to get here, and then we did partial fractions on that remainder. And there's our final result, x minus 4 plus 3 over x minus 2 over x minus 1. Now these partial fractions, they're basically just a lot of algebra moves. It doesn't require knowledge that we've gained recently in most cases, depending on what you were just looking at recently. But it is something that is useful, a useful technique to have for studying calculus. But I do want to mention that lots of people think that partial fractions and knowing how to do partial fractions, learning how to do partial fractions, that's left over from a time when we didn't have access to calculators and other things at our disposal that could do things like this for us. So there are people now who say that now that we have calculators that can do partial fractions, that Wolfram Alpha, if you don't know that website, you should, that can do partial fractions very nicely. So the overall moves that we've learned have been just algebra, and it is useful for what you'll probably be doing in the future. And I cannot guarantee you that someone in the future won't require that you know how to do this. I'm just letting you know that it isn't something that is really widely considered to be a useful mathematical concept. We have technology. I mean, I wouldn't ask you to multiply 8-digit numbers to each other or divide two decimals. I would say punch that into a calculator. And you know what? I think this is maybe something that fits into that category too. But I love algebra. The algebra moves are great. And this is something that you might have to use and know how to do by hand in the future. So you got to go that route as well. But know what tools are at your disposal for doing things like this. And if you have access to those tools, you should go ahead and use them.